n. So now we're going to define a Fibonacci function, fib of n. And we'll go here, paste this in. Oops, pardon me. Paste this up here and run it. And of course, fib's not defined. So we'll go up here and we'll define fib of n. And the Fibonacci numbers, as you can see here, are defined such that each Fibonacci number, say 5, is the sum of the previous two. 2 plus 3. 21 is 13 plus 8. So the nth Fibonacci number is simply the n minus first Fibonacci number plus the n minus second Fibonacci number. This is clearly a beautiful application of recursion. That is a beautiful definition, which unfortunately doesn't work. Because we stack overflow as we knew we would because we don't have a base case. So if we're in our base case, which naturally would feel like if n is 0, return 1 because that's our first Fibonacci number. There it is right there. Otherwise, go ahead and dive into our recursive case. That still doesn't work. It looks like it would work, but alas, let's think what happens. If I call fib of 0, sure enough, base case, wonderful. But if I call fib of 1, when n is 1, it's going to call fib of 0 plus, and here's the problem, fib of minus 1. It jumps our base case. Because it goes by 2s, you must have 2 base cases to catch that. So we'll have n is 0 or n is 1. Or if you prefer, you could simply say if n is less than 2. That works. So that is recursive Fibonacci with a slightly more interesting base case.